Esta wea, vale.
And what we can look at here is where our 22 hits right there, and ask what percentage of these tosses would be that big or bigger. And we get here for the binomial distribution, that's 0.8%. Right? And this actually, if you've heard of these p-value things, this is actually a p-value. We have a p of 0.008 for the data that we looked at. That says that assuming the null hypothesis is true, assuming there's no effects that we're interested in, the probability of getting our data just by chance is 0.8%. And we can say this is less than 0.05, which is the arbitrary bound that someone long ago decided was the right bound to set, and therefore our coin is not a fair coin. Now, this is nice, and this works for a lot of people, but I find that many people who think in code, who think about the world procedurally from the standpoint of writing Python code, there are other approaches that might be more helpful. So, for example, why deal with all that binomial distribution thing when you can just simulate it, right? We can do a loop of 100,000. We can do a loop of 100,000 repetitions. We can draw a random integer, 0 or 1. We can ask what the sum is, and if it's greater than or equal to 22, we add 1 to the result, and we find that 0.008% of, or 0.8% of the time, 0.008, we get this result of 22 heads or more, right? So we've just done in 5 lines of Python code what we did previously in a few slides of mathematics. And the point I want to make here is that you all have a way of looking at the world as hackers, right? And you can express some of these statistical ideas in this language that makes intuitive sense to you. The other way works well, right? The other way works as well. But for many people who think about the world in code, I think this is a really good way to solve this problem. All right, so in general, computing the sampling distribution, that's this binomial curve that I showed you, is a difficult thing to do. But also, in general, simulating the sampling distribution can be very easy. So what I want to do today is I want to show you a few recipes for doing this sort of simulation of the sampling distribution, so you can answer statistical questions appealing to the types of coding intuition that you have. So this first one, direct simulation we just saw, that works well when you have some a priori model of the world, like you know that a coin toss is going to land 50% of the time, and you can simulate that. But even in cases, as we'll see, even in cases where you can't get an a priori estimate of what the outcome will be, we can still do some sampling approaches. So the next one I want to talk to you about is shuffling. And sticking with the Dr. Seuss theme, I don't know, does anyone know who these guys are right here? These are one of my favorite Dr. Seuss stories, the Sneetches. So the Sneetches were this group of creatures, and half of them or so had stars on their bellies, and the other half didn't. And over time, those with stars on their bellies started to think they were pretty special, and lorded over the rest of those Sneetches without stars upon theirs, right? So let's say you are a researcher, and you want to go in and answer whether the star belly Sneetches really are better than those without stars upon theirs. You might go in and administer some sort of test, right? So here's a distribution of test scores you give to the Sneetches out of 100 points, and the Sneetches with stars have a certain number, without stars have a certain number. You compute the means of those, and you find that the star-bellied Sneetches have a 73.5% average, and the non-star Sneetches have a 66.9 average. So obviously, 73 is higher than 66, but the question you should be asking is this significant? Could it just happen by chance, right? And I want to say that this section that I'm going through here is drawn from an excellent talk by John Rouse he gave a couple of years at an O'Reilly conference. So he didn't do the Sneetches, but he did something very similar. So is this significant? And you can do this the classical way. If you go back to your Stats 101 and kind of read the table of contents, so remember that there's this thing called a t-test, and what you do is you subtract the means and you divide by some weighted sum of the standard deviations. So we can do that. We can plug in our numbers and we get 0.93, right? All right, so what does this mean? You go read a little further in your Stats 101 text, and you see that this t statistic should be distributed this way, right? And that upside-down L shape there is a gamma function, and the little v-shaped thing, that's a Greek letter nu, which means degrees of freedom. And you scratch your head and you're trying to remember what degrees of freedom are, and you go to Wikipedia and it says the number of independent ways by which a dynamic system can move without violating any constraint imposed on it, and you're like, okay. But then you dig a little further, and down the Wikipedia page they say that this Welch-Satterthwaite equation can get you there. So you know how to plug numbers into a formula, and you get 10.7. So that's your degrees of freedom. And then you go to a chart like this, and you look up 11-ish degrees of freedom for a 0.05, and you find that the t statistic is 1.79, and you have to ask if your t-value is greater than that. And remember, we computed the t-value way back. It was like 0.9, right? And this is not true. So the difference of p6.6 is not significant at the p equals 0.05 level, right? Excellent. And you sit back and you're like, I did it. So the problem is we've entirely lost track of what question we're answering, right? I know there are probably a few statisticians in this room for whom that logic makes sense and helps you understand the problem. I'm not one of them. I don't know. You may not be one of them either. But so what we can do, some people might say, well, why are you going through all that mumbo jumbo when you can just do this? You just import t-test in from stats models and plug in the right form of the variance and the right form of everything else, and you get out a p-value. But again, this might be the right level of abstraction for some people. It's not the right level of abstraction for me, and I guess for a lot of folks in this room, this is not a helpful level of abstraction for writing a question. Because the problem is, what question is this answering? If you're 4 years into a statistics degree, you might be able to answer that off the tip of your tongue, but I certainly can't right now. So stepping back, we go back to this. This is the real key of this problem, the sampling distribution, the student's t distribution, and it's very similar to what we did before with the binomial distribution, where we're asking how often do we get 22 heads with a fair coin. Here, what we're doing is we're drawing a different type of distribution, and we're asking for the cutoff and trying to integrate everything above the cutoff. So why don't we use a sampling method instead, something that you and I can wrap our minds around? Well, the problem is, unlike coin flipping, we don't have a theoretical model. We can't simulate a Sneetch, right? All we have are these test scores. So we need some way for those test scores to be the simulation themselves. And what we can do in this situation is something called shuffling. So the idea here with the shuffling is that we're going to simulate the distribution of possible test scores by shuffling these labels around. And the motivation is that in the null hypothesis, if star-bellied Sneetches and regular Sneetches are really the same, it shouldn't matter what the labels of these numbers are. So we can label them however we want. So this is what we do. First we shuffle the labels. We've kept the numbers in the same place and just shuffled around the red and green squares. We rearrange them, take the mean and the difference, and we can plot it on our little graph there. We got a difference of 4.8. Then we do it again. We shuffle the samples, we rearrange.